There's a secret language to the universe, and it's written in atoms. Everything around you, the screen you're reading this on, the air you're breathing, even your own body, is just atoms having conversations. Atoms consist of a nucleus made of protons and neutrons and electrons zipping around. The number of protons defines the element. Add or remove one, and you get something completely different. This is hydrogen. This is oxygen. Combine them and you get water. This is sodium. Now, I wonder what happens when sodium meets water. Oh, bad idea. Don't try this. Quantum mechanics tells us this is not what atoms look like. They look more like this. But hold that thought. We'll dive into the quantum stuff later. Let's talk about electron shells. Picture these like layers around the nucleus, holding electrons at different energy levels. The outermost shell is particularly important because it contains the valence electrons, and these are the ones responsible for most of the chemical reactions we see. Atoms want their outer shell to be full of electrons because this makes them more stable. For most elements, this means 8 electrons in the outer shell, except for hydrogen and helium, which are fine with just 2. The periodic table is arranged in such a way that elements in the same column have the same number of valence electrons. This is key to understanding why certain elements behave similarly in chemical reactions. The periodic table itself is like the ultimate cheat sheet for understanding all the elements. The rows of the table tell us how many electron shells an atom has, and the columns show us how many valence electrons are in those outer shells. By checking the group number, you can get a pretty good idea of how an element will behave in a reaction. For example, alkali metals all have 1 electron in their outer shell, which makes them highly reactive, sometimes explosively so. Moving down the table, elements get heavier, gaining more protons, electrons, and neutrons, and they become more reactive as well. Next, we have ions, which are atoms that have a charge. When an atom has an equal number of protons and electrons, it's neutral. But if it gains or loses electrons, it becomes charged. If an atom gains electrons, it has a negative charge and is called an anion. If it loses electrons, it has a positive charge and is called a cation. These charged atoms are eager to bond with other atoms to form compounds, and this is where the magic of chemical reactions happens. Ions are like the little actors in the play of chemistry, constantly interacting with one another. Finally, when 2 or more atoms bond, they form a molecule. If those atoms are from different elements, the result is a compound. What's fascinating about compounds is that they often behave in ways that are completely different from the individual elements they're made of. Take table salt, for example. It's made from a highly reactive metal and a toxic gas, yet when they bond, you get something harmless. Molecules are often represented by formulas, where numbers show how many atoms of each element are involved. But here's where it gets interesting. 2 molecules can have the same formula, but different structures, which are called isomers. This explains the difference between graphite and diamond. They're both made of carbon, yet their properties couldn't be more different. Atoms bond because they all want the same thing, a full outer shell of electrons. This is the ultimate goal, the perfect balance. They bond in a few different ways to achieve this. First, there's the covalent bond, where atoms share electrons, like 2 people sharing a blanket on a cold night. Then, there's the ionic bond, where one atom gives up an electron, and the other grabs it, making one positively charged and the other negatively charged. It's like a swap meet of electrons. And lastly, metallic bonds, where metal atoms share electrons freely in a giant electron party. They're all about the collective good in a giant atomic dance. Covalent bonds can be tricky though. Sometimes the electrons are shared equally, and you get a non-polar bond, like a perfect team of equals. But sometimes one atom is a bit more selfish, hogging the electrons. This creates a polar bond, and suddenly you have a molecule with a positive side and a negative side, like water. And that polarity is exactly why water is such a great solvent. It's like a molecular matchmaker, breaking apart charged particles and pulling them into solution. Speaking of water, its polarity makes it an absolute super solvent. It can dissolve all kinds of stuff, charged molecules, salts, sugars, you name it. But if the molecule is nonpolar, like oil, water just can't do its magic. This is why oil and water don't mix. But here's a fun twist. Soap. Soap molecules have a polar head and a nonpolar tail, so they can grab oil and carry it away. Think of it like a tiny superhero cleaning up your mess. Now let's switch gears a bit and talk about the states of matter. We all know three basic states: solid, liquid, and gas. But matter has wilder forms. Plasma, which is like the rock star of matter, super hot and ionized. You'll find plasma in stars and neon signs, lighting up the night. Temperature and energy play a huge role here. The hotter something gets, the more energy the particles have, which leads to more chaos, or entropy. Chemical reactions happen when atoms decide they can rearrange themselves to be more stable and at a lower energy level. There are a few main types of reactions: synthesis, decomposition, single replacement, and double replacement. These all follow stoichiometry, which is just a fancy way of saying we balance the atoms to make sure nothing gets lost. It's like making sure every pizza at a party has the right number of slices. No one gets shorted. And speaking of moles, no, not the little creatures digging in your yard. We're talking about the unit used to count atoms.
1 mole is 6.022 times 10 to the power of 23 atoms, and it's exactly the number of atoms in 12 grams of carbon-12.
This helps us figure out how much of each substance we need for reactions. It's like figuring out how many pizzas you need for a party, but instead, you're calculating how many atoms you need for a chemical reaction. Now, chemical reactions need a little push to get going, and that push is called activation energy. It's like the initial nudge you need to get a sled moving down a hill. Without it, reactions would just sit there, doing nothing. Enter catalysts, the unsung heroes of chemistry. They speed up reactions without being consumed, kind of like a cheerleader helping the team score but never getting tired. Without catalysts, many reactions would take forever or require way too much energy to be practical. Think of them as the shortcut that makes chemistry way more efficient. Some reactions release energy, and we call these exothermic reactions. Imagine burning wood in a fireplace or watching fireworks explode. That's energy flying out. On the flip side, we've got endothermic reactions, which require energy to get started. Like photosynthesis in plants, where sunlight is absorbed to make food. We can track how much energy is released or absorbed using something called enthalpy, and if we want to know whether a reaction is spontaneous, we look at Gibbs free energy. If it's negative, the reaction happens on its own. If it's positive, you're going to need a little help to get things moving. When it comes to acids and bases, it's all about protons. A proton is just a hydrogen ion, H+, and acids and bases are basically in a constant battle of passing them back and forth. Acids are generous. They love to donate protons, while bases are more like protons' biggest fans. They love to accept them. The strength of an acid or base depends on how much proton action they're involved in. A strong acid releases a lot of protons, while a weak acid barely does. We measure this using the pH scale. A pH of 7 is neutral, think pure water. Below 7 is acidic, and above 7 is basic. So, when you get that sour taste from lemon juice, that's your acidic protons at work. Redox reactions? They're all about electron transfers. This is where things get juicy because it's a constant game of who's losing and who's gaining. Oxidation is when an atom or molecule loses electrons, and reduction is when it gains electrons. These reactions are happening everywhere, from the oxygen you breathe to the fuel burning in your car's engine. It's a simple but essential process that powers life itself. And then there's quantum mechanics, the part that makes your head spin. Electrons don't just orbit around atoms like planets in a solar system. Instead, they exist in probability clouds, and where they show up is anyone's guess. These clouds are defined by quantum numbers, which tell us the electron's energy, shape, and location. It sounds mind-boggling, and it is. But trust me, we'll dive deeper into this quantum wonderland soon. For now, just know it's incredibly fascinating and honestly, a bit of a science magic trick. And that's the incredible world of general chemistry. Atoms, bonds, reactions. It's all connected in the most mind-blowing ways. Remember, chemistry is all about understanding how everything fits together and how we can use it to our advantage. If this video sparked your curiosity, hit that subscribe button and drop a like. Got questions or thoughts? Leave a comment. See you in the next video, where we break down even more chemistry craziness.